see a lot of smiley faces, and as always, Oliver is smiling even more than everybody else, and so is Bertrand. Great to see. Yeah, maybe we should start, and then I'll just let people in as they come along. I'll just get my screen ready here. Okay, so good morning, good afternoon, and good evening. We are streaming now across at least some 17 time zones. So this has been a great thing to organize. There's been so many people that have been willing to help out and participate. So, so we're really thrilled to be able to do this event. I'll just mute again, I think. Yeah. So welcome to the first virtual annual meeting of the IGCP 653, the onset of the great Ordovician Biodiversification event. I am Christian Rasmussen, as some of you might know, and together with my co-organizers, Alycia Stigall in Ohio, and Arne Nielsen and Sven Stoke and Niels Skovsbo here from Copenhagen, we are really looking forward to welcoming you all and to have these next 4 days of hopefully fun events with a lot of cool science. We have so far, we do have 45 presentations, and we are about 160 registered for the conference. At least that's the latest number I heard of. Alycia, you may correct me if I'm wrong.
We're up to 183.
Ah, okay, so a bit more than that. Okay, so it's pretty nice. We are, yeah, about 70 in here now, so so that's pretty good. We should, of course, have been in Copenhagen, and that's not really what's the case now, I know. So we should have been here. I hope you can see the lovely Geological Museum, which is in Copenhagen. This should have been our venue, and we should have been situated in this nice botanical garden with this, I don't know if you can see it, Victorian style, yeah, what do you call it, greenhouse here. So this should have been a really, really nice venue. And to make things even worse, we actually have an excellent dinosaur exhibit just this year. So Tristan Otto is here, and of course that would have been in the very same building. So while we had coffee breaks, we could have gone, watched this amazing T-Rex. And so for those of you who have fear of missing out, I'll just show you some more pictures of this great dinosaur because it's really a fantastic fossil. These are just images I took with my iPhone the other day. But still, yeah, we couldn't be here. We couldn't be in Copenhagen. Here we also have the Rosenborg Castle, which is where we had the crown jewels, and the Geological Museum is just behind this. So this is a really, really nice place. However, yeah, it says instead behind me. Instead of going there, we are actually here now. So let me just zoom in if I can. We have Copenhagen here on our on my right at least. This is Copenhagen, Greater Copenhagen area, and over here we have the Botanical Gardens. Here you see Rosenborg, Geological Museum, and the Botanical Gardens. But instead, we are out here live streaming from a cluster of houses called Sorø. This is where I sit right now. So I'm not in Copenhagen either. But thankfully, I just got a new internet connection. So I'm actually sitting right here watching that trampoline right now. So this is where we're live streaming from. Not exactly Copenhagen, but yeah. Technology nowadays makes wonders, I know. So this is not the official closing meeting of the IGCP network, and we're not into dinosaurs after all. So this does, of course, mean that it's okay for us to meet in this virtual setting. We have placed the meeting in the same dates as originally planned, which I think is great because that's probably why we are so many people that are able to join. But in case this thing blows over, this pandemic, we have actually already started to organize a meeting, or rather a Copenhagen meeting in late May, so you should remember that. But yeah, we'll see how things turn out. I should also say that as we got extended 1 year for the IGCP network, Thomas is actually organizing a final meeting, or a absolutely final meeting in September in Lille. So if we are lucky and we actually get to meet each other in real life, then we can actually have 2 meetings next year. But let's see how well this turns out. For this meeting, we have tried to do everything as informal as possible. Probably we are a bit naive, but we chose to do it this normal meeting way instead of using Zoom's webinar option, because that would be more like people talking, giving a talk, and then nothing else. Here we can actually talk, all of us, which is going to be fun. I think it's also a bit risky, of course, because we can interrupt each other at all times. So I, as the administrator, I'll try to mute all microphones, but once there's questions, you can either raise your hand digitally down here in the options that you see on your lower bar. You can choose, I can't even find it, maybe it's in reactions. No, no, it's to your left. If you open your chat, then you can raise hand, I think. And then you can also, if you want to say something, you can press the space bar and then your microphone will unmute. You can, of course, also just unclick the microphone image on your left. So that was a bit about the practicalities. I can also say that once we go to the coffee break, we will create breakout sessions just completely randomly, I guess 5-10 people in each, so that you may either go for coffee or talk to the people that are randomly put together with you. And in order to, and also further enhancing this informal setting, we have been so fortunate that Birger Schmidt has offered to give us a tour of his lab on Thursday. So while there's a coffee break, we actually go to see Birger's lab in Lund, which should be quite fun. And we have actually forgotten one thing in the program. I come to think of that now, and that is, of course, the icebreaker. We have no icebreaker. So if any of you are in the correct time zone after this last session today, I will keep the connection open, and I will have a beer for sure. So yeah, we can sit and have an informal chat if anybody wants. And that reminds me to also say that by that time, I will shut off the recording session, because there's no need to record that. But while we have the talks, we will be recording, and then we will be posting all the sessions in YouTube, on YouTube, so that those of you that are either sleeping now or in other meetings or something else, you'll be able to catch up on these talks at a later time. Yeah, so there are a lot of things to say here. Yeah, so there's also a chat. Some of you might have noticed on your right-hand side, you can open the chat and you can ask questions, and we will try to catch your questions and answer them as best as we can. Yeah, so this, of course, does not replace the physical meetings. We know that, but given that this actually permits so many other people to participate, this is a great way to meet now that we don't have the chance to meet in person. So there are also advantages with this digital era. Before I hand the word over to Thomas, who I hope is here somewhere, Thomas, who is the official leader of this IGCP 653 network, I'd just like to take the opportunity once again to thank you all, because you have all been great. It has been an overwhelming support, and even though I have been late in the planning, whenever I write to any of you, you always respond yes. So that has been great. That goes all the way for keynotes to whatever. I have been asking basically last week or whether you had the time, and you have. So that was fantastic. Also the moderators invited last minute, all of them, but still, you were great. I would also like to thank my co-organizers, Arne, Sven, and Niels, and especially Alycia, who basically overnight built a website. When we first talked about this in late June, she had basically already created a website. And even though she's 6 time zones behind us, she was always basically ahead of us in the planning. So that has been fantastic. Thank you a lot, Alycia, and thank you to the rest of you. As everything is streamed through my computer, I have removed all kinds of notifications on my computer. I hope that they don't pop up all the time. And I have at least tried. I also hope that everything works. What could possibly go wrong, right? But there's no plan B. So with those words, I will hand the word over to you, Thomas, if you are there.
I'm here.
Fantastic.
Do you see me?
Nope.
Well, my camera is there.
I think it's just my. You're here, yeah.
And so everybody can hear me, probably, should work. So Christian gave me half an hour, but I see that there are only a few minutes left. I will be very short. So for all information on IGCP 653, you can of course go to the web page. Short reminder to those who don't know us. So IGCP is International Geological Correlation Program, but now it's called International Geoscience Program. So they are numbered from 1 to something like 700 now, chronologically. So 653, that's our number. Most of you, or some of you, remember 410. This was the beginning of all this. This was the IGCP that went from 97 to 2001, plus an additional year 2002. This was the Great Ordovician Biodiversification event. This was followed by 503 that went from 2004 to 2008, plus an additional year on extended term 2009. This was the climate and paleogeography driven one. This was followed by 591, a little bit larger, early to middle Paleozoic revolution from 2011 to 2015 plus 16. And then we focused again on the Ordovician with the current one, the onset of the Gobi, 653, that is running from 2016, and now we are in the final year. So we had all leaders agreed to have a main annual meeting. So first one was in Northern England that Dave Harper organized in Durham with excursions to the English Lake District. 2017, Wan Dong organized a meeting in Yichang. 2018, Alycia organized the meetings in Ohio. 2019, together with the Ordovician Subcommission Novosibirsk, we had the International Ordovician Symposium organized by Olga Obud and Russian colleagues. And now this meeting, we are in the final year, but online, virtually, with Christian Rasmussen organizing this meeting, but hopefully we will have the meeting for real next year in May. So usually these meetings are, these IGCP programs are running for 5 years, and usually we had a 6th year. So it was originally planned, also not announced, because we have first to ask for it to get the extended term. But it was planned to have an extended term next year with a meeting in Lille with excursion to Wales and France and Belgium. So this is already announced. You can see it on the web page of, so hopefully next year we will have another meeting. You will have some more news coming for IGCP and a possible successor project that is currently discussed at the closing ceremony of this meeting. So try to be there at Thursday again. And then you will get some more new information. This meeting shows us that when we go online, we have much more participants than if we are really attending physically. And this is maybe also something for the future, that maybe we should have more of these virtual meetings, because it's impossible with very little budget, because IGCP budget is something like between 5,000 and 10,000 US dollars. It's impossible for us to pay, for example, people from Iran, from Uzbekistan, from Argentina, or from Zimbabwe to come to our meetings. So maybe we should do in the next years a mixture of these virtual meetings. And I hope we will have a successful meeting now here. And I thank very warmly Chris and Alycia, who have the logo behind their heads of this meeting, to having organized this, and also the Danish local organizer. Thank you very much. And I hope that we will all have an enjoyable meeting. Thank you very much.
Thanks, Thomas. Yeah, well, so I think we are just a few minutes ahead of time, and I know Rebecca is already online, so I think we are almost ready for you, Rebecca. I would just, of course, I forgot one thing is to refer you all to the conference code of conduct, and so how we should behave here online. There's so many people together in this digital forum, and you can find these documents online on the conference webpage, and you can also find all sorts of information on how Zoom works and all these things. So I only see Thomas on my screen. It's maybe because he wasn't muted. I don't know. I hope it's working. But I think we can move on to our first speaker, which is Rebecca Freeman. I think that's a perfect way to start this conference, with you, Rebecca, starting as a speaker. And Rebecca is going to talk to us about late Cambrian biotic immigration events, or BIMEs, Vicariance, and Extinction patterns in Laurentian Lingulform Brachiopods. So, Rebecca, go ahead.
Okay, hopefully I'm unmuted. I'm still getting used to this Zoom world. I've been teaching online now for a couple of weeks of the semester, and it still seems like every Zoom meeting starts with technical difficulties and everybody's saying, can you hear me? Can you hear me? So hopefully you can hear me. All right, so as Christian said, I want to talk about brachiopods, Lingulform brachiopods in the late Cambrian to earliest Ordovician of Laurentia. And I have to say this sort of takes me back to the Durham meeting, because I was actually, I think, the last or the next to last speaker in the Durham meeting. We were running way behind time, and I kind of had to cut the talk short. And I joked at the time that I would give the second half of the talk at the next meeting, and that never actually happened. So you would think I would be finally given that second half of the talk, but instead I'm actually going back to think about some of the things that I was talking about 4 years ago in Durham. And I really like this logo that you guys have come up with for multiple reasons. Zooming in on the goby, haha. Also, I like this sort of metaphor of a lens, because for me, this is what this project has really been about, which is that we all have our little areas of research that we really focus on, but it's been wonderful in this project to sort of share in other people's research and have a better sense of like what's going on internationally in terms of looking at issues that are related to things I'm studying and so on. So I really do like this logo. All right, so I'm going to be talking about the time from the late Cambrian into the earliest Ordovician. Of course, there have been many updates since this famous Sapkowski figure, but I always like to include it. It's a classic. It could also be a drinking game, how many times we see this figure at some point during the seminar. But it's, what I really like to focus in on is that time period between the Cambrian explosion and the Great Ordovician Biodiversification event. In the US, if you go to Geological Society of America meetings, there's Friends of the Cambrian. They have like a party, and then there's Friends of the Ordovician. And I always feel left out in both, because Cambrian people tend to focus on early to middle Cambrian, and Ordovician people tend to focus on the Gobian past. And I'm really interested in that diversity law between the two. And as we know, this was probably a pretty bad time to be a marine invertebrate. It was a time whenever ocean temperatures were unusually high, and there's increasing evidence that there was a lot of ocean anoxia going on at the time. And this certainly had something to do with it. In Laurentia particularly, and we're starting to see this as more of a global phenomenon and not just Laurentia. Whoops. This interval was characterized by a series of trilobite extinction events. And these trilobite extinction events have been used to define stage boundaries in Laurentia. And so currently, 5 of the late Cambrian into early Ordovician stages are bounded by these trilobite extinction events. And there are 5 of them that I study, but I'm going to really focus in on the middle 3. And unfortunately, of the 5, 4 of them start with an S, so they're easy to get confused. And also, I show range charts. I'm trying not to show too many range charts because I know they bore people, but I always color code them. So we've got the yellow one, the turquoise, and the purple one, even if you don't care to remember North American stage boundaries and names, since most of you are not in North America. Just think of them in terms of colors. All right, so back in the day, my master's degree advisor was Jim Stitt at the University of Missouri, and he was very interested in this interval, and he was a trilobite guy. I was his only Brachiopod student ever. And even though he didn't come up with this idea of BIMEs, and that was P. Palmer, Stitt did a lot to study this idea. And this is from his classic paper in 1977, where he's showing the ranges of trilobites. And you can see that at each of these stage boundaries, you have a very abrupt extinction of the trilobites. And then often what would happen would be that a trilobite would appear that seemed to be from outside of the basin. There would be a regional radiation, things would be fine, and then there'd be another trilobite extinction event. People are really focused on the trilobites, partly because they're more numerous and abundant than brachiopods, partly because they're sort of like the dinosaurs of the Cambrian. They're somehow considered more glamorous than brachiopods, which I don't get, but anyway. And Stitt, in that same paper, he hypothesized that these extinctions were caused by some sort of change in the oceanographic conditions. And his 2 hypotheses were either cold water or anoxic water had caused environmental conditions to change in the shallow shelf environment, which would then cause those trilobites that were living on the shelf to go extinct, and colder water trilobites or deeper water trilobites to move up onto the shelf environment. Stitt unfortunately died pretty young of cancer, and I've always thought it was sad that he didn't get to live to see that his hypotheses are really supported by a lot of the interesting geochemical work that has come out in the last several decades about ocean anoxia during this time period. All right, I mentioned the whole lens idea. I've been thinking about this and working on this for a very long time, but I have to say that one of the really good outcomes of this particular project was, getting us exposed to other people's research and thinking about that. And so 2 papers that have been particularly influential on me have to do with Alycia Stigall. So I think of this as like the Alycia lens. Alycia and her students, who are now really awesome scientists in their own right. And so one of the things I've really started thinking about this in terms of Alicia's idea that to increase biodiversity, you need to have speciation. And we have 2 sort of models of how this could happen. One would be a biotic immigration event, or BIME. So you have a species, part of it migrates to another location, it's isolated, and new species evolve. But we also have vicariance, where a population gets subdivided, and then those 2 subdivided populations then evolve into new species. And so as Alycia and her students have pointed out, when you have an alternating regime of these types of events, this can really allow diversity to build in a hurry. And so I want to sort of think about this when I'm studying before the Gobi in terms of this. And then last summer, Alicia's paper about the hierarchy of invasion, the idea that we can see invasive species in the fossil record. And as she points out, these invasions can be at all different scales. We can have everything from ephemeral invasions, where they just show up, they don't really have a long-term effect on the ecosystem, or basically no effect at all, and they go away quite quickly, to the global scale of invasion, where you have invasive species on the global scale that's a major disruption to the ecosystem. So I wanted to sort of look back at some of this and think about it through, as I said, the Alycia lens, and think about what I'm seeing here in the late Cambrian earliest Ordovician. So as I said, I'm going to particularly focus in on these 2 intervals here, the Steptoean to Sunwaptan stage boundary, which is an extinction event, and the Sunwaptan to Skullrockian stage boundary here, which is also an extinction event. All right, so the study areas are all in Laurentia, and 2 of the study areas in the US states of Utah and Nevada are out in what's called the Great Basin area of Laurentia, which is deep subtidal outer shelf environment. They're in the purple. And then we also have the US states of Oklahoma and Texas in the orange, which were more of a shallow subtidal type of environment up on the craton. So contrasting environments in these 2 places. Let's start with the Steptoean. During the time the Steptoean strata were being deposited, this particular brachiopod, Linarcinella girdii, was extremely widespread in Laurentia. Pretty much everywhere you find rocks of that age, you find this brachiopod, and often in great abundance. Laurentian Lagartii is endemic to North America, both at the genus level and the species level, but it seemed to be extremely happy during this time. And as I said, you find it all over the place in Laurentia, very uniformly throughout Laurentia. When we get to the top of the Steptoan, we see evidence of the trilobite extinction event. And right about the time the trilobites abruptly go extinct, we have the appearance of 2 new species in the Great Basin, that deep subtidal shelf environment in Utah and Nevada. And the first of these is the acrotreated Quadrosonia minor, shown here. And we also have a Zanatella, Zanatella rotunda, that appears about the same time in the same strata above the extinction of the trilobites in the very early part of the San Juan. And the thing that's special about these 2 species, besides the fact that they're lovely little brachiopods, is that unlike Laurentian Lagartii, which is endemic to North America, these species have a fairly global distribution. So they're found not only in the Great Basin, but also both of them are found in Kazakhstan. Zanatella rotunda is found in strata in France that belong to Gondwana. And then Quadrosonia minor has possibly been reported from the Precordillera region of Argentina, which of course could have been part of Laurentia. So a global distribution instead of being endemic to North America. But at the same time, in Texas and Oklahoma, in our cratonic shallow subtidal environment, we do see the sudden extinction of trilobites and the ubiquitous Laurentian Lagartii, but the replacement fauna in Texas and Oklahoma is not globally distributed. It continues to be endemic to Laurentia. And so all these species on this is the one range chart I'm going to show you, and this is from Texas. And all the ones that I've labeled here in orange, these are ones that are endemic to Laurentia. And some of them have also been found in Montana through the work of Grant in 1965. And they're really weird. This one I put in here particularly, it's an acrotreated that looks like its dorsal valve merged with the human foot, really weird little brachiopods. So after this first extinction event, the Lingulform brachiopod community was split into 2 very distinct biophases, where you'd had one very widespread one before. So during the early San Juan, on the Craton was a new fauna, but still endemic to North America, whereas out on the shelf in the deeper subtidal environment, the fauna was quite different and clearly had ties to Gondwana in Kazakhstan. Now, by the time we get into looking at the middle and the upper San Juan strata, again, I'm showing you the Texas range chart. I'm sparing you all the details of all the range charts. But by the time you get into the sort of second half here, the species that we find in the 2 study areas, the deep subtidal and the shallow subtidal, are very much in common. The fauna in the deep subtidal environment is a little bit more diverse, but the species that are found there are also found in Texas and Oklahoma. So we sort of merge biophases again as we get into those upper San Juan strata. Thinking about Quadrosonia minor, which first shows up around the time of that extinction, the first extinction event, Quadrosonia minor seems to give rise to a whole series of Quadrosonia species that are endemic to North America. Up here at the top, in the Utah-Nevada deep subtidal environment, there's a series of overlapping ranged species of Quadrosonia that are found only in that area. Whereas in Texas, in the shallow cratonic environment, we have another species of Quadrosonia, and these are all endemic to North America. And throughout most of the San Juan, it seems that you had 2 very different populations of Quadrosonia in the Great Basin versus in Texas. And so it seems that this original Quadrosonia population got geographically separated, and we have speciation through vicariance going on here. Towards the top of the San Juan, though, we start to see the same Quadrosonia in both places, Quadrosonia lavadamensis, so wider spread in Laurentia, but still Laurentian only, not globally distributed, before we get to the next extinction event. And the same with Zanatella rotunda, it's globally distributed. It appears about the same time as the extinction in the lower San Juan, and it's replaced by a new species of Zanatella, Zanatella utahensis, which is endemic to North America only, or Laurentia only. And it too goes extinct at the next extinction event. So our second extinction event is the one that marks the San Juan Skull-Rockian boundary in Laurentia. And right after this extinction event, another acrotreated appears, Eurytreta sublata. And like Quadrosonia minor before, Eurytreta sublata is globally distributed. We find it not only in the Great Basin and Texas, I should point out, and Oklahoma. We find it in Kazakhstan, and we also find it in Iran in strata that were part of Gondwana. So very similar to what we saw in the aftermath of the first extinction event, we have globally distributed brachiopods. Another sort of intriguing clue is that in the lower skull Rockian strata in all of the study areas, we get the first Siphonotretids that have spines. They're almost always pretty fragmental, which is sad because they clearly were beautiful brachiopods. It would be nice to know what they really looked like other than just fragments. But this is intriguing because they've also fairly recently been reported from what seem to be exactly equivalent strata in Iran and Gondwana. And so these are the two oldest known occurrences of Siphonotretids of hollow spines. And while I'm not sure if they're the same genus and species, due to the fragmental nature of their preservation, they clearly are closely related. We have this sort of this innovation that appears at the same time in both places, which seem to indicate some sort of migration from one place to the other. All right, so thinking about these two extinction events that were followed by migrations of globally distributed species, I wanted to think about them in terms of Alycia's hierarchy of invasion and think about where they might fit into her hierarchy here. And so thinking about the Septoan to Sunwaptan extinction followed by invasion, I think that this one would be considered isolated invasion. It was fairly short-lived. These species showed up and they were relatively short-lived, and they were only found in the outer shelf deep subtidal area. They were not found on the craton. But the Quatersonia minor gave rise to a whole lineage of Quatersonia species that were endemic to North America, or Laurentia, that split into separated populations so that we had speciation by vicariance as the habitat got split up. The Sunwaptan skull Rockian extinction followed by invasion seems to fit more into Alycia's coordinated invasion. In this case, the BIME affected both the deep subtidal shelf area and the cratonic shallow subtidal area. So not just one region of Laurentia, but seemingly the whole area along the coastline. And then kind of like what we saw with the Quatersonia previously, Eurytreta shows up. It appeared earlier in Kazakhstan, so it almost certainly came from Kazakhstan. It shows up in Laurentia, and then it also becomes the dominant acrotretid genus and gives rise to a series of species, some found also globally and others endemic to North America. It also seems that after the second wave of extinction followed by invasions, the community seems to have not bounced back as well. It seems to be less diverse than it was during the Sunwaptan. And so as Alycia points out in her students, the BIMEs could be associated with both increases in diversity, where you have a population, you're adding new species to it, but it can also cause extinction where they outcompete the ones that were originally here. But in this case, the invaders seem to be showing up either during or after the extinction events. And so it seems like these late Cambrian to earliest Ordovician BIMEs were opportunists and not necessarily competitors. They may have been taking advantage of a situation where the landscape was sort of wide open for them to come in and settle and establish. And so it's interesting that we can demonstrate that during this time, we have both these BIMEs going on and also speciation through Vicariance. So the things that we know that were that some of the driving mechanisms for increasing diversity during the Gobi seem to be going on during this interval. But it seems that the periods of extinction dampen the diversity. And so we know that diversity did not increase during this time, despite all these episodes of alternating BIMEs and Vicariance. But it seems that the environmental conditions of the Cambrian to earliest Ordovician continually dampened biodiversity through extinction events. As we all know, we can't get a Gobi until we have more speciation going on than extinction events. And so with that, I'll ask for questions and awkwardly try to figure out how to bring you all back visible. I think I'm back.
Thank you. And thank you for taking us back. That was an excellent talk, Rebecca, and very, very interesting. And also from an interval where we don't know a lot of stuff, right? It's, as you say, much is focused on the spice event and much is focused on the middle Ordovician part and upwards. So this is really insightful to get this Laurentian view. I should ask, are there any who has any questions for Rebecca? Alycia, or no?
So Rebecca, this is all really very cool. And of course you're focused on the Brax, but I know you also know about the trilobite patterns to some degree. Do you see similar patterns in the trilobites, or is the information not as clear for those clades?
I think it's there, and that was actually going to be something I was going to do this summer, was really dig into the trilobite literature and see if I could put that together, but we all know what happened this summer. So I didn't quite get there, but the research that I did do before the pandemic hit and I suddenly had a bunch of needy online students on my hands, it does seem like it's there, and it's something I really want to delve into in the future, definitely.
Awesome, thank you.
I've got one if that's okay.
Joe?
Yes.
Yeah, it's interesting. I really noticed that east-west divide that develops in the between the brachiopod faunas in Laurentia, and it just suddenly struck me. I'm trying to remember the details now, but in sponges around, I think it's the early Ordovician, you see a similar thing, where you get a sudden sort of division into eastern faunas, western faunas. We've been sort of puzzling over why that might be, if there was a continental, a current change or something like that was going on. But I don't know if you have any thoughts, if you notice that the same thing happens in other groups as well, or might be something to look into if not.
Well, there are a couple of possibilities. Certainly they were different environments. In Texas and Oklahoma, it's evidence it's very, very shallow water, very high energy. And in Utah and Texas, it clearly was much deeper. So it could just be a difference in the environment and how the brachiopods were adapted. But there's also, if you look at reconstructions for Laurentia at that time, there is the possibility that there was this landmass that actually separated those areas. There's also evidence that that didn't exist, but a lot of reconstructions of Laurentia have a landmass sort of separating that shallow cratonic area from the deep subtidal area. So it could have been a paleogeographic barrier, and even if that landmass didn't exist, it could have been also an area that, that was so shallow that it prevented migration easily or something like that. But yes, I think it's curious that you do have this, like, everything's the same everywhere, and all of a sudden they're subdivided, and all of a sudden they're back together again. So yeah, I've puzzled over that many times, and I don't really have a definitive answer for that.
Okay, are there other questions for Rebecca? I don't see any digital raised hands or anything, so I will just thank Rebecca for this great talk. And then we should move on with the next speaker, which will be this meeting's first keynote. And this is a presentation by Adriane R, Sarah Sheffield, and Nicholas Matzke. And she has sent me a presentation digitally, so I will see if I can somehow find it here on my computer. I thought I could the other day, but now I can't. So that will just take a second, I think. It's here. So, see if I can. I'm just gonna stop share 1 second and see if I can do it like this. I think that works better. Yeah. So here comes Adriane. Adriane, who's going to talk about estimating dispersal and evolutionary dynamics in the diploporan blastozoans, Echinodermata, across the Great Ordovician Biodiversification event.
Christian? Christian, I think you need to share the audio also.
Hi everyone, thank you so much for tuning in this morning or afternoon, depending on where you are tuning in from. Our talk today will explore the biogeographic patterns of a group of Paleozoic echinoderms, the diploporan blastozoans, across the Great Ordovician Biodiversification event using novel methods. One of the great benefits of having this conference online this year is that we are able to welcome so many new folks into this conference, like students who may be new to the field. Since that is the case, we wanted to start with a broader introduction to the Great Ordovician Biodiversification event, or the GOBI for short. The GOBI, occurring across the Darwinian stage of the Middle Ordovician, represents a threefold increase in family-level diversity and a fourfold increase in generic level diversity across planktic, benthic, and tectonic life forms. Some invertebrate groups are better studied for their diversification patterns across the GOBI, such as the brachiopods, trilobites, and conodonts. Echinoderms, although they broadly show similar diversification patterns, are not as well studied in this context. As echinoderms are a highly diverse and disparate group, their diversification patterns have the potential to shed additional insight into speciation processes and paleobiogeographic patterns before, during, and after the GOBI in response to abiotic processes. Speaking of abiotic factors, there are several hypotheses for the explosion of life that occurred during the GOBI. Explanations for such a drastic increase in diversity include increasing atmospheric oxygen levels, decreasing global temperatures, and increased weathering from areas such as the tectonic highlands, which potentially drove higher nutrient delivery to the epicontinental seas. To date, it is still unknown if and how these abiotic processes affected echinoderm evolution. Few studies currently exist that have explored blastozoan evolution, their paleobiogeographic patterns, and the abiotic drivers of such patterns. Such studies by Lefebvre and others, and Nardin and Lefebvre, indicate that the blastozoans did increase in diversity through the Ordovician, and that endemicity was low throughout the period. These studies, however, are limited in scope as they were conducted at coarse temporal resolutions without the context of phylogenetics. In this study, we investigate the speciation types and paleobiogeographic patterns of diplopore-bearing blastozoans through the Ordovician. Blastozoan echinoderms are a large grouping of stemmed, extinct echinoderms from the Paleozoic. There are multiple groups within blastozoa, and each are identified by a specific type of specialized respiratory structure, which are quite disparate in form and function from one another. Different types of blastozoans, such as the blastoids, eocrinoids, and diploporans, are identified by different types of these specialized respiratory structures. However, recent research of the morphologies of these structures has indicated that convergent evolution in these groups are likely, meaning these groups, likely based on delineations of respiratory structure types, are very likely not representing natural evolutionary groupings. Therefore, any previous studies of echinoderm biogeography need to be re-examined in the light of true evolutionary groupings. In diplopore-bearing blastozoans specifically, organisms are identified by diplopores, a simple two-pore system, such as a species in the center. However, many have modified diplopores, such as the specimen here on the right, whereas others have secondarily lost diplopores, such as the specimen pictured on the left, which has no respiratory structures at all. Additionally, some non-related, non-blastozoan groups, such as Edrioasteroids, do have diplopores. Although diploporans have long been suspected to be a polyphyletic grouping based on the diverse morphology of the respiratory structures, no rigorous phylogenetic analyses have been done to test this hypothesis until most recently. Sheffield and Sumrall, in their 2019 study, presented the first phylogenetic hypotheses of diplopore-bearing taxa. There are three major groupings of diploporans: spheronatids, glyptospheratids, and astroblastids, each color-coded here and illustrated by their representative taxa. The only true clade is the spheronatids, here indicated in red. Overall, the diploporans are polyphyletic, indicating that diplopore respiratory structures are homoplastic and have been lost or gained more than once throughout echinoderm evolution. How many times this trait has been lost or gained has not yet been directly tested and isn't pertinent to our conversation here. Since Diploporida is not monophyletic, we cannot treat it as such for phylogenetic biogeographic analyses. Therefore, we use the phylogenetic hypothesis presented on this slide to better understand the paleobiogeographical patterns of those echinoderms with diplopore respiratory structures. In this study, we used the character matrix used to construct the Sheffield and Sumrall tree to investigate both speciation types and paleobiogeographic patterns for the diploporans before, during, and after the Gobi. We used the R package BioGeoBears, which is an open source package written by our collaborator, Nick Matzke. The package reconstructs ancestral states within a phylogenetic context, and using an additional method within the package, we will also reconstruct and investigate dispersal directions among defined basins. One thing that BioGeoBears requires is a geography file with defined areas. In this study, we defined 8 basins, 6 of which are within Laurentia. These Laurentian basins are split and defined based on thermal and physical barriers, such as the transcontinental arch. The basins also follow invertebrate and microfossil provinces within the paleocontinent. Our other 2 areas include Baltica and Gondwana. The second thing BioGeoBears requires is a fully bifurcating tree topology. Therefore, the character matrix from Sheffield and Sumrall was subjected to Bayesian tip dating methods within the program BEAST2. This allowed for a resolved topology and provided more realistic divergent states for the species. On the left of this slide is a tree with minimum age dates and ranges of taxa taken from the paleobiology database and published literature sources, whereas the tree on the right is a topology after being subjected to tip dating methods. BioGeoBears provides models mirroring the assumptions from 3 previous historical biogeography programs, allowing them to be compared in a common, likelihood-based framework. These are dispersal extinction cladogenesis, or DEC, dispersal vicariance analysis, or DIVA, and Bay Area. Because DIVA and Bay Area are slightly modified from their original programs, they are called DIVA-like and Bay Area-like within BioGeoBears. These models allow for geographic ranges to evolve along branches within the phylogeny using range expansion or dispersal, and range loss or local extirpation. Each model is also modified with a +J parameter to model the probability of founder event speciation or jump dispersal within the phylogeny. Founder event speciation is sometimes termed speciation through long distance dispersal or allopatric mode 2 speciation. This is when a small number of individuals are subjected to a rare long distance colonization event in which a new population is established that is genetically isolated from the ancestral population. Strong winds or storm systems, birds, oceanic rifting, drifting or rafting can all behave as dispersal vectors. Founder event speciation has been important in oceanic island systems. So for example, through molecular phylogenetics, Schweitzer and others in their 2015 paper found that jump dispersal was an important speciation process in New Guinea parrot lineages throughout the Neogene. We also conducted biogeographic stochastic mapping into our analysis. This method, which is implemented within BioGeoBears, allows for the estimation of the number, percentage, and direction of dispersal events within the phylogeny. This method was used in a study by Dupin and others to infer dispersal events and directionality for nightshade plants. In the table here from Dupin and others, geographic areas are represented along the top and left sides of the table. Directionality is determined from the left to the top. So in other words, the left side of the chart represents areas that are ancestral areas, whereas those along the top are areas species dispersed into. If we look at one of these boxes within the table, such as the one outlined in the bolded black box, we would interpret this as 48.6 dispersal events that took place from South America to Central America. This result is represented by the large arrow in the figure on the left, which I've outlined with the bolded red box. In this study, we were interested in both range expansion and jump dispersal events and how these changed through the Ordovician. Therefore, we time sliced the BSM analysis to better determine how speciation patterns and dispersal paths changed before, during, and also after the Gobi interval. The first time slice encompasses the Termidocian to the Dipingian stages. The second time slice is the Darwinian stage and the Gobi interval. And the third time slice encompasses the late Ordovician Sandvian to Hernandian stages. As indicated earlier, BSM has been implemented in other studies, but our study is novel in that this is the first time BSM has been used on an all-fossil phylogeny and the first time that it has been time-sliced to best resolve evolutionary patterns through time. The 6 models, which were DEC, diva-like, and beta E and J parameters, indicate the rate of dispersal, extinction, and relative weight of jump dispersal in each model, respectively. For the diploporan phylogeny, the diva-like plus J model fit best. In all cases, the addition of the plus J parameter improved model fit. This finding indicates that jump dispersal was needed to fully explain biogeographic patterns within the clade. We use the diva-like plus J results to further interpret evolutionary and paleobiogeographic patterns in this group. What I'll do next is step through the results of the diva-like plus J diploporan tree. This is our time-calibrated phylogeny against the 2016 geologic timescale. Species names are at the tree tips, along with colored boxes that indicate which basin that species occurs. BioGeoBears reconstructs the most probable area relationships at the nodes within the tree, and that's represented by pie charts. Each colored slice of the pie chart represents an area and the likelihood that the ancestor lived in that area. If we zoom into one of these nodes, we see that this pie chart indicates the shared ancestor most likely lived in the Cincinnati Basin, which is represented by this blue color. There is about a 25% probability that the ancestor came from the Southern Appalachian Basin, represented by that purple pie slice. When we take the most probable area from each node to further interpret evolution and dispersal patterns, we see that for this example, the most probable area here is indeed the Cincinnati Basin. Now that we have the phylogeny with the most probable area reconstructions, we can then infer vicariance and dispersal within the tree. Dispersal is inferred when descendant species occupied a new area than that of its ancestor. Vicariance was interpreted when the descendant species occupied subset areas from that of its ancestor. But I do want to stress that this eyeballing method is not the best method to infer speciation events, because it does depend on the most likely areas ancestor species occupied. However, mapping these dispersal and vicariance events on a tree is helpful when we compare the timing of events to geochemical datasets, which we'll do a bit later. The biogeographic stochastic mapping method is the best method to infer speciation types across the tree. And here are those results. From the biogeographic stochastic mapping, the number of event histories were sampled within the phylogeny across all area histories. Here it is apparent that dispersal processes, both founder event or jump dispersal, as well as range expansion events, were most important to the evolutionary history of blastozoan diploporans. Jump dispersal was dominant in each time slice over range expansion, with very little vicariance occurring. The result that founder event speciation was a prominent speciation process is also true for other Ordovician clades, such as Brachiopods and trilobites. Models that allowed for founder event speciation best fit the brachiopod phylogenies of Sensulo and Stigall, the strophomenid phylogeny of Congreve and others, and 4 brachiopod phylogenies of Lamb and others. The same was also true for 6 species-level phylogenies from Lamb and others for trilobites. Because dispersal events, both range expansion and founder events, were so prevalent from the BSM analysis for the diploporan tree, we focus the rest of the paleobiogeographic interpretations on the range expansion and founder events. As mentioned earlier, the BSM analysis can also indicate directionality of dispersal events among basins. In this table, directionality is determined from the left to the top. So the left side of the chart represents areas that are ancestral areas, whereas those along the top are colonized areas. The numbers in the boxes indicate the number of events that occurred between 2 areas, with the standard deviations in parentheses. Within the table, areas that have the most dispersal events are indicated by the darker colors, whereas lighter colored boxes indicate lesser dispersal events. Below each table of events, I've also included dispersal maps to best visualize what is going on in each time slice. Arrows on the map indicate directionality of events, with bolder lines and arrows on the maps corresponding to the darker colors in the table. In this first time slice of the early to middle Ordovician Tremodosian to Dipingian stages, this is when the most dispersal among paleocontinents occurred. Namely, the majority of dispersal events took place between Baltica and the southern Laurentian Basin, which is present-day eastern Canada. There was also increased dispersal among Laurentian basins, namely between the western mid-continent and the southern Appalachian Basin, or more simply put, the western and southeastern United States. Moving into the Darwinian stage in the Gobi interval, there is less dispersal that occurred during this time compared to the early to middle Ordovician time slice. However, like the early to middle Ordovician, there is still increased dispersal from Baltica to Laurentia via the Cincinnati Basin, as well as a strong path from the western to southeastern US. Dispersal still occurred between Gondwana and Laurentia and Gondwana and Baltica, but that occurred on a lesser scale. The last time slice encompasses the late Ordovician Sandvian to Hernantian stages. Generally, the dispersal patterns here are very similar to those of the Darwinian stage. Within this interval, the most dispersal occurred again from Baltica to the Laurentian Cincinnati Basin. Increased dispersal events are also apparent from the western US into other Laurentian basins. One of the other major questions is, what are the abiotic factors that influence blastozoan speciation and dispersal patterns? We can preliminarily investigate this question by comparing our speciation events, as inferred from the tip data tree as shown on the right of the slide, to geochemical records and model results. In this slide, we have plotted global mean sea level in meters above present day, carbon-13 and oxygen-18 stable isotopic time series, the mercury to total organic carbon percentage, and various models of atmospheric oxygen through the Ordovician. So now we've plotted the speciation events, which are all dispersal events, from the phylogeny against the abiotic data. It's quite apparent that these dispersal events are about evenly spread through time, which makes it quite difficult to infer what Earth system processes were most likely contributing to blastozoan diploporan speciation processes. However, it is apparent that long-distance dispersal was occurring throughout the entire Ordovician within the clade, especially during the early to middle Ordovician. In 2016, Pohl and others modeled Ordovician surface ocean circulation under different atmospheric carbon dioxide levels. For their early and middle Ordovician intervals, it is apparent that the Ordovician ocean was characterized by gyre systems operating between continents. These gyre systems, as well as upwelling zones, likely operated as dispersal vectors for blastozoan diploporans. Since we have the data plotted for the blastozoan diploporans, we can compare their evolutionary events to those reconstructed for the brachiopods and trilobites. Again, it is hard to determine any similarities or differences among these marine invertebrate groups because of the smaller number of blastozoan speciation events compared to brachiopod and trilobite events. But in general, it seems that the Ordovician invertebrates relied mainly on range expansion and founder event speciation processes compared to Vicariance speciation. Further directions will include a larger sampling of blastozoan species, especially so that we can better compare and contrast evolutionary patterns of blastozoans against brachiopods and trilobites. Additional phylogenetic hypotheses will also further elucidate the relationship between marine invertebrate evolution across the Gobi and abiotic factors that drove a diversity increase. There is also geographic bias that occurs in our dataset, from some areas, such as North America, being more heavily sampled than other regions. Additional sampling and specimens incorporated into phylogenetic hypotheses could remove some of this bias and further shed light into evolutionary patterns. There are also additional analyses that could be conducted within BioGeoBears itself, such as increasing the resolution of the BSM analysis to more finely determine speciation patterns across major paleoclimate shifts. As a concrete example, further work to understand blastozoan evolutionary patterns in the context of paleobiogeography is currently being done by ourselves and our colleagues. We are utilizing smaller data sets of blastozoan eocrinoids and rhombiferans, primarily Cambrian in age, and subjecting those to similar methods presented here to better constrain biogeographic patterns in the Cambrian, as well as potential rates of diversification. This may help us better understand things such as paleoecological triggers in the development of traits like respiratory structures. Many hypothesize that the trend seen in the convergent evolution of diplopores, also seen in other blastozoan groups, is due to extrinsic paleoecological pressures. We can begin to compare these different data sets to one another to gain a better grasp on how echinoderms are diversifying throughout the early Paleozoic and how these patterns may elucidate the morphological trends that we see. So stay tuned for that research. So just to wrap up and conclude, this is the first study to investigate Ordovician diploporan blastozoan speciation and dispersal patterns within a rigorous statistically informed phylogenetic framework. Our study is also the first to implement a time-slice BSM analysis on an all-fossil phylogeny. We found that founder event dispersal was likely a critical evolutionary strategy for echinoderms, and has also been found to be important for brachiopod and trilobite clades. Throughout the Ordovician, long-distance dispersal took place among the major areas defined in the study, but namely took place among Laurentia, Baltica, and Gondwana. Such long-distance dispersal was likely influenced and facilitated by oceanic gyre systems. Lastly, additional data in the form of new species incorporated into existing phylogenies and additional phylogenetic hypotheses of shallow marine invertebrates will help to further understand the drivers of evolution across the Gobi. Lastly, we'd like to acknowledge funding from the Cushman Foundation for Foraminiferal Research, Joanna M. Riesig Fellowship to myself, funding from the Paleontological Society's Arthur J. Bucco grant to Sarah Sheffield, and funding from the National Institute for Mathematical and Biological Syntheses, the U.S. Department of Agriculture, and the University of Tennessee Knoxville to Nick Matzke. Thank you all for your attention, and I'm happy to answer any questions at this time.
Thank you, Adriane. Yeah, so does anybody have questions for Adriane Lam and colleagues? That was a really great talk. By the way, yeah, I also have some applause here. So if nobody else has any questions, Adriane, I would just like to hear one question here. So you say you have most data from Laurentia, but even so, you still find invasions from Baltica all the way through the Ordovician. Is that understood correctly?
Yeah, we did. We found a ton of the dispersal happening from Baltica to Laurentia in most of the time slices. So there's a really strong signal between those two paleocontinents. And we think that might be part of the geographic bias. But this is a reason why we really need more data, more phylogenies, to really test that and see if is that sampling bias or is that a pattern we're actually seeing. But in our 2018 paper, we also found this really strong connection between Baltica and Laurentia as well. So I'm thinking that that's actually a real pattern.
Yeah, I certainly agree with that. So I guess there's not much going the other way, right? From Laurentia to Baltica, or what?
No, we found a few dispersal paths from Laurentia into Baltica, but that path like from Baltica into Laurentia is definitely the most prevalent and the strongest for sure.
Okay, and even so, before the Derivilian, if you go into the Trimidocian and into the Pinkian, is that the same pattern all the way through, I suppose?
Yes, it is. We see that like at all three time slices from the early to the late Ordovician, which is interesting.
Yeah, that's interesting. And it's also, I guess, it's something we see in other clades also, right? So this is certainly interesting. Are there anybody else who has any questions for Adriane? I think we still have a few minutes. I'm still here. Yeah, somebody is saying something. I think I'm busy trying to admit people into the room.
Yeah, I think there's a question. I'm sorry, I might pronounce your name wrong. Guyan?
Yeah, actually, I have a small question about the model selection. Basically, if I get it right, it seems that you got 3 models and do model selection. But based on the results, seems the DC and DV-like model, the AIC value is quite similar. So I'm not so sure why you still your interpretation is mainly depends on the based on the DV-like model. I think maybe how about the DEC model and what's the difference between those two models. I'm really curious. I'm not so familiar. Maybe more backgrounds about those two.
Yeah, no, that's a great question. There wasn't much difference. So when I looked at the models with the pie charts and then the optimized areas at the nodes, there was only one node that differed, and I can't remember what basin was more prevalent over another, but they were essentially almost exactly the same. So that's why we just went ahead and chose the Diva-like plus J model to base our interpretations on. But no, that's a great question because they were really close. And we've run a few other models on other phylogenies where we have the same thing happen. And usually when the model fits are so close, we kind of just go in and check out what's different. And if it's just, you know, one or two nodes that differ, we just go ahead and use the model with a slightly better fit. But yeah, it's definitely something to pay attention to that we've thought about for sure. Good question.
And thank you.
Yeah, thank you.
So are there other people who have some questions for Adriane? If not, I will thank you once again. This was a great keynote. And then I think we should move on to our next speaker, who's also my co-organizer, Alycia Stigall. And she will give a presentation about how did invasion events promote evolutionary and ecological change during the Great Ordovician Biodiversification event. Yeah, go ahead, Alycia.
All right, so first of all, try to make sure I'm sharing properly. Okay, so has that shared properly? Are we actually seeing the full slide? Okay, excellent. Well, so thank you everyone very much for joining us at our virtual conference. Christian and I and the other organizers are just so thrilled that you could all be here and that we have this forum to share our science and gather, even though we can't really come together in person. And the upside of having the ability to really bring together the entire global community, because there's no cost barrier, the way that a standard travel is, has just been a tremendous benefit of this format. So what I'd like to talk with you about today is a little bit about some of the concepts that I'm very fortunate that Rebecca and Adriane have already shared this morning, and thinking about how the goby can really fit within some of these concepts of diversification and invasion. So I'll start off by talking a little bit, just to remind everybody already knows what the goby is. We've been talking about it all day, and of course that's the whole project. But I would like to just point out a couple core things. When we talk about the goby, what we're really describing is a biotic pattern of diversification. And that pattern is explicitly tied to a major ecosystem reorganization. And that has explicit biogeographic components. So we can see this very stark increase that is centered here in the main pulse of the goby around the Dipinian-Darwinian stage. We see that we go from kind of limited ecosystem complexity in the Cambrian to high complexity by the time we hit the middle to late Ordovician. And we can see that there are dramatic changes in the geographic distribution of organisms through this time. And my colleagues, Christian Rasmussen, Cole Edwards, and Rebecca Freeman and I published a review that really dug into some of the details of how these biotic changes relate to abiotic changes in the environments last year in PaleoCubed. And so if you haven't had a chance to check that paper out, that's this here. And so look at it if you'd like. Let me see. Okay. All right. So when we think about the goby, then we're talking about an evolutionary pattern that has ecological and geographic features. And of course, I like to talk about brachiopods. And so today I want to think with you about how all three of these features really work together to think about how diversity increases. And in addition to that, I want to pause a little bit and think about the difference between microevolution, which is where we have population and organismal level change, and how that differs from the macroevolutionary patterns of genus, species, and family level diversification that characterize the goby. So we really want to think about kind of that it's really at the level of organisms and populations where we have to have that gene flow breakdown in order to actually separate out genetic lineages to build new species and genera and then clades. And so thinking through those things today, I want to talk a little bit about invasions. We've been talking about dispersal through Rebecca's talk, tremendously through Adriane's talk. And I just want to remind you what happens during a dispersal event. So a dispersal event fundamentally is an invasion event. You have a taxon, in particular a population that is present in one place on the earth. That's where it evolved, that's where a population has grown, that's where it's in concert with other organisms in the ecosystem. Some component of that population manages to become transported across some geographic barrier. Now, about 90% of those organisms typically die, but maybe some become established. And if they become established and then rapidly go extinct, that might be an ephemeral invasion, such as we saw an example with Rebecca this morning. But maybe that population becomes permanently established and even spreads within a local environment. And then we might have an isolated invasion where we have some organisms that establish a population, but it stays local. But some of those organisms, potentially those that have more generalized ecologies, might actually spread and disperse out of that basin. And maybe a bunch of them do it at the same time even, and we can have a coordinated invasion. And if that continues to spread to additional geographic areas, we may get to these higher levels of interchange or global invasion. Now, the key point is that most invasions fail before we get to these large-scale issues. But these large-scale ones can have major impacts on ecosystem structure and function. So let's look at what these different invasions actually do. So as Rebecca showed this diagram earlier, but when we think about ephemeral invasions, this is just where you've got some individuals, they make it through, they stay alive, but they go extinct, and there's really no changes to the ecosystem. So you might just see like a coral, for example, showing up in one layer and then going away again. Whoops. And an isolated invasion, this is more of a community accommodation feature where you've got boom and bust. You might have thousands of these organisms in a single bedding plane. Now, isolated invasions are great for biostratigraphy. These are things like epibole beds. We can use them as markers, but they typically don't persist beyond a very short stratigraphic interval, so they don't really change the ecosystem in the long term. A coordinated invasion, on the other hand, is where we might have many, many different organisms from multiple clades that really come in at the same time. A good example of this is the Richmondian invasion from the Cadian of North America. In this case, we have organisms including brachiopods, corals, cephalopods, trilobites, all that kind of move in at the same time using different oceanographic currents. When that happens, the community structure fundamentally shifts. And we have changes in niche partitioning. We have a lack of speciation for a while as we deal with a bunch of generalists basically out competing specialists for a short while. As we move up to the next level, we can think about interchange invasions. And this is something where you have two components or two faunas that mix together, maybe more than two. And we have major changes to large scale extinction and speciation rates, and fundamental changes to ecosystem structure. The Great American Biotic Interchange is a beautiful example of this. We have mammalian faunas that mix, and afterwards, the South American mammalian fauna is fundamentally changed from the fauna that was present before the invasion. At the very largest scale, we have faunal homogenization at global crisis levels. And so this might be something like the Hernantian glaciation, where we have the Hernantian fauna moving around, we have this faunal homogenization, or the late Devonian. We see changes at these large scale global ecosystem structures. What I want to argue with you today is that the Great Ordovician Biodiversification event fits the hallmarks of an interchange invasion. And what has been really nice for me today is that you've seen examples of this from the prior talks. So Adriane and Rebecca have both been talking about the fact that we've got a lot of dispersal, a lot of invasion at this time. We've also been talking about these fundamental changes to the environment, going from the Cambrian fauna-dominated world to the Paleozoic world, in which we have much more diverse ecosystems. So we have fundamental ecosystem changes. We have dramatic changes in evolutionary rates. So just to kind of look at that in a little bit more detail, this is one of my favorite charts, which is a chart from Dave Harper and colleagues' paper a while back from the last IGCP project, really summarizing what we know about both the diversification of the brachiopods across the Ordovician. You can see this big increase here from the Dipingian, the Darwillian, but also the geographic changes. And so this part that Christian put together, you can see here we've got different colors showing what clades are prevalent. We'll just look at Laurentia for an example. So here in Laurentia, you can see we've got lots of purple and a little bit of orange. But it's in the early Ordovician, and some other continents have relatively limited types of diversity. As we move over into the Gobi interval, you can see that there's an increase in the number of clades. You can also see that paleocontinents like Laurentia and Baltica start actually to look a bit more similar to each other. And then as we move into the late Ordovician Cadian, you can see that we've actually got a more substantial diversification on these paleocontinents at the different family and ordinal levels. So how does this happen? Well, we can think about this within a diversity cycle. And we've talked about BIMEs a little bit today, but I want to just pause for a moment and explain how this basic pattern of diversity ratcheting can occur by interchanging invasion events or biotic immigration events with separation of basins during vicariance. And so we start in this example, let's say we've got 4 basins. They each have a single species. We have an invasion event, biotic immigration event, in which these basins get connected, species can move around, but what they don't do at this phase is actually diversify. When you move things between basins, in this model, we're assuming that you've maintained some genetic continuity, and it's not until you get to the following phase where you disconnect these basins once again that we actually then have that speciation. So the founder event speciation that Adriane was talking about requires a phase of dispersal and then isolation. And so we see that kind of happening here. So in the vicariance phase, we can get a new species forming in each basin. So if we look at the blue line down at the bottom, this is global diversity. So going from the initial phase through that immigration event, nothing's really happening. It's not till you get the vicariance that we really increase that diversity. If we repeat that then, we can then move our species around again, no new species until we separate those basins. Now let's get 2 new species per basin because we're much more diverse. And you can see that when we do that, we're really building up this the global diversity very, very significantly. We're also increasing the local diversity, which is shown here in red. You can see there's many more species per basin. But the important thing for the Gobi isn't what's happening in a single basin, it's what's happening across this global pattern. So we can see that by cycling these dispersals and invasions against these separations, we can actually get that ratchet functioning. So if we look at the data that we have for brachiopods, you can see that in Laurentia, we've got a pattern of increase, then a plateau, and then an increase. We can see that pattern in Baltica, an increase, plateau, and an increase. We can see something like this in Gondwana. We've got an increase, a bit of a plateau, and then an increase. So matching this diversity ratchet, this cyclicity. And of course, as I mentioned, when we look at these patterns, we can also see that there are differences in who's present, what are the clades. And by moving those clades around, you can see that we start off with some differences in our paleocontinents, and then we end up with much more similarity as we move those different clades around through all the different paleocontinents kind of sequentially. Now we want to look at whether or not that really relates to this Gobi pattern of diversification. And this is from Christian Rasmussen and colleagues' sample standardized curve of diversification through time. And you can see that really we have this strong increase here in the middle Ordovician. And then Björn Kruger and his colleagues looked at the rate of net diversification. Again, you can see that there's not a constant diversification through time. There's something very specific happening during this Gobi or main pulse of the Gobi interval. So what's happening? Adriane just walked us beautifully through biogeobears and how that pattern works. These are some additional results from my former student, Shalyn Sansulo. This is her master's thesis work, and we're working on getting this published. But what I want to point out is that there are some pretty brachiopods, and these are species level phylogenies. And again, you can see this alternation of vicariance and dispersal through time, demonstrating that as we move through this Gobi interval, these are middle Ordovician brachiopods, that you move through this kind of ratchet cycle. So we've got a lot of data for this at large scale, but also at the very fine level. If we look at the dispersal pathways, reconstruct Shalyn's phylogenies that we just looked at, you can see that these are early Ordovician dispersal pathways. In her clades, there's a lot of movement within North America. When we get to the middle Ordovician Gobi interval, we start to move into increased dispersal. In these clades don't live so much in Baltica, but they move into Avalonia. And by the late Ordovician, these clades are all going extinct, so there's not much to say there. Looking back at a figure that Adriane showed us, these are a series of brachiopods and trilobites that she worked on previously. And again, this is the Gobi interval. And again, you can see lots of intercontinental dispersal operating in her Dipingian and Darawillian time slice. Okay, so just to step back for a moment, why is this happening? So we can demonstrate with data, of course, that we've got this diversification. We can demonstrate that we've got this peak in rates. We can demonstrate that we've got speciation and dispersal happening. But what are the Earth conditions that are really promoting these changes? And so if we look at what's happening on the Earth, there's a lot going on in the abiotic world. We have changes in plate tectonics that demonstrate an increase in continental weathering. We've got a dramatic decline in temperature in the global oceans that move for the first time into the present sea surface temperature range. We've got an increase in oxygenation. We have a variety of excursions going on in the carbon curve, and we have a series of sea level rises and falls. Now, all of these changes set the stage, or initiating or facilitating conditions. They set the stage to increase biomass. They allow organisms to build shells and to increase the shelly component of the fauna, but they don't on their own really diverge. Things like increasing oxygen and decreasing temperatures on their own don't diverge genotypes. They don't separate out the genetics. We need something to actually cause that vicariance, allow that dispersal. And the best way to do that really is to think about sea level. So as sea level rises, we can have dispersal. As sea level falls, we can build vicariance. We also have been talking a bit this morning about the makeup of the continents. What is the tectonic regime? The fact that we have island arcs that permit these jump dispersals. So there's a lot going on, but it's really, we've got these facilitating conditions that come into play for really the first time in this middle Ordovician world. And then we have these, really kind of causal factors that actually produce the vicariance, allow the dispersal. And that biogeographic factor is really what allows this ratchet of diversification to operate at this time. So just to summarize, invasions are really common in the fossil record. And they occur at all sorts of different scales with all sorts of different impacts depending on their position in the invasion hierarchy. There are significant environmental changes that can facilitate diversification, and we do see these happening during the Gobi. This alternation of vicariance and dispersal then provides this kind of ratchet that fosters diversification at this time, particularly in the Darawillian, and we can therefore classify the Gobi as having the hallmarks really of this interchange invasion. So in conclusion, or finally, I would just like to acknowledge collaborators for this project. The project IGCP 653, as mentioned this morning by Rebecca, it's just been such a fantastic opportunity to bring together scientists from the biotic world, the abiotic world, all different angles of thinking about the Ordovician. And that's been just tremendously wonderful to think together with all of you across all of these meetings. And I look forward to continuing to do so in the next year. And so thank you very much. And I'll go ahead and stop sharing and take any questions.
Thank you, Alycia. That was a great talk. You get my applause immediately here. Are there anybody who has any questions for Alycia? There seems, let's see, well, Keegan maybe, yeah.
Yeah. I actually have a small question about the invasion event. I mean, do you have any idea what's the major factor of this invasion? It's a biological one, like we have new type of larva, or what kind of factors behind this dispersal and invasion event? Do you have any idea?
Yeah. Right. So, you know, when I think about the invasion events, I'm always thinking about that flow chart about how most invasions fail. And so when, you know, when I think about why they're succeeding, what I think about really is, you know, so we're mostly dealing with organisms, at least the ones that I study most intently have, you know, larval dispersal. And so what is allowing the larvae to succeed at dispersal, to succeed at settlement at these particular times? And so I think that a lot of it has to do with oceanographic changes. You know, as we move into sea surface temperatures that don't kill the larvae to start with, moving into the cooler temperatures is important, but also the oceanographic pathways are shifting as we move into the more cooler world of the Middle Ordovician. So I think that we really just have a lot of those kind of really, I would say most of it's probably the oceanographic impacts of the cooler temperatures, the changes in the circulation and things like that. And then the sea level rise and fall on top of it.
I come up with this question just because during the Cambrian and Ordovician boundary, and we see this new types of larva of gastropod, and we have some kind of this report. I'm just curious about is there anything similar happening in your group in this stuff?
So,
I mean,
you know, there may be, and I will say that brachiopod larval biology, most of our clades are extinct. And we do see major changes in kind of the dominance of clades. The orthids are around and the orthids stay around. They are, you know, dominant in the Cambrian and they stay so. But we have these other clades that do come in and rise to prominence. And brachiopod workers argue quite a bit about exactly what type of larvae we've got in some of these clades because we simply just don't have modern examples and their early shells are not always clear. But it's a really good question, and that's a good possibility, actually.
Thank you.
Yeah.
Thank you.
Thank you, Kikan. Are there other questions for Alycia? I think, yeah.
We're on time.
We are on time, yeah. It's very unexpected. Of all the unexpected things that we expected, this was not one of them. So I will move on with the next speaker, who I will find somewhere on my desktop. It's Fernando, and I will do the same thing as I did before. I think if I can get it working, I will just open it and then go back, stop sharing, and then find this window here, hopefully. Is it still not showing? I don't know why. This is Adriane. Yeah, then I just have to show it like this, I think. So how are you seeing this? I'm just gonna check here. I was hoping to get it into a window. Now I think it works. Yep. But there's
Fernando Lavie from Argentina, and
Does
I will
it
talk
sound
about of new contribution on the.
I don't think there's sound on, is there? Yo, now there is. Sorry for So start over, and then it should work.
Hi to everyone. I'm Fernando Lavie from Argentina, and I will talk about a new contribution on the paleobiogeography of Lingulform Brachiopods from Ordovician of the Precordillera Argentina, in collaboration with my director, Juan Luis Benedetto. As a very brief introduction, in the recent years, several analyses on the biogeographic distribution of Ordovician Lingulform Brachiopods has carried out, where the works of Popov and others in 2013 and Holmer and others in 2016 stand out. In this presentation, I am going to show the results obtained from the analysis made during my doctoral thesis. The main objective of this study was to reassess the biogeographic affinity of the middle and upper Ordovician Lingulform genera recorded globally, including the new data from the Precordillera of Western Argentina. So the Precordillera is a geological province of nearly 500 kilometers in length. It is characterized by a thick Cambrian Ordovician carbonate succession deposit on a low latitude and passive marching platform. The Precordillera is located in the inlayers of the southern central Andes. It is limited to the east by igneous and metamorphic rocks of the Sierras Pampeanas, and to the west with the Cordillera Frontal. Geographically, it is located mainly in the San Juan province, as well as in the southern area of the La Rioja province and in the north of Mendoza province. In addition, the Precordillera, along with other calcareous outcrops, the San Rafael block, located to the south in the province of Mendoza, constitute the Cushania terrain. The material used for this study comes from 9 localities in 5 different formations, namely San Juan, Gualcamayo, Las Chacritas, and the lower member of Las Aguaditas formation, all from Middle Ordovician age. The material collected from the Upper Ordovician comes from De las Plantas formation and from the middle and upper member of Las Aguaditas formation. Here on the map, you can see the location of the sample section. So, 2 generic richness tables were created, modified from Holmer and others in 2016. One for the Middle Ordovician with 49 genera from 9 regions, another for the Upper Ordovician with 43 genera from 9 regions, both excluding endemic and cosmopolitan taxa. These data were updated with several works on Lingulform Brachiopods systematic from the Precordillera made in the last 5 years. For each one, clustering analysis and principal coordinate analysis were performed using the DICE and Route Creek indices and using the program PASS 3.05. The results obtained from the analyzed Middle Ordovician times in the Cushania terrain shown strongest affinities with Baltica, Laurentia, and the Kazakhstanian terrains, which are constant for both analyzed and both indices. The only difference is that with the DICE index, a close relationship with the New Zealand region is observed, while with the Route Creek index, it is more related to the South China region. The results obtained for the Upper Ordovician time-lapse show disparity between both indices and also show a great difference with respect to the observed in the Middle Ordovician. Using the DICE index, the Precordillera doesn't have close affinity with any region, and it appears almost isolated. While with the Rock Creek index, the Precordillera already shows clear Gondwanic affinity, probably because this terrain was in a stage of accretion to the supercontinent. Here you can see a paleogeographic reconstruction during the middle and upper Ordovician time, based on Scottish in 2016, showing the hypothetical distribution of the major Lingulform cluster obtained from the analysis. Finally, some conclusions and comments emerge from these results. During the middle of Ordovician, many of the genera from the Cuyana terrain show clear Laurentian and Baltic affinities, sharing with this region at least 13 genera, excluding cosmopolitan and widely distributed taxa. Additionally, there are several genera in common with the Kazakhstanian terrains. But by the late Ordovician, however, despite the scarcity of data at global scale, as Popov and others in 2013 pointed out, many genera become restricted to Laurentia and are absent in Argentine Precordillera. The distribution pattern and paleobiogeographic affinities of the Lingulform brachiopods of the Argentine Precordillera is similar to that observed in other benthic faunas such as trilobites, bivalves, and Rinconiform brachiopods. This pattern may be due to the fact that late Middle Ordovician, Upper Ordovician time, the Cuyana terrain was already close to the western margin of Gondwana, the so-called pre-accretion stage. Then, thank you very much for your attention.
Thank you, Fernando. And let me just excuse that I was a bit confused that I couldn't find the file, but it was of course Fernando and Juan Luis Benedetto who gave this presentation. I'm sorry about that.
It's okay.
It was an excellent presentation. Are there any questions for Fernando? If not, then I have one, I think, because this is a very peculiar continent. So you say that that the faunas look different down through the Ordovician. When do you start seeing these first Gondwanan genera in your matrix?
Sorry, I don't understand by the audio. What do you say?
No, but I was just thinking, when do you start to see? So basically, Precordillera is moving the direct opposite way of everything else at this time in the Ordovician, right?
Yes.
So I was just wondering, when do you have any sort of evidence of when you start to see genera from the south in your microterrain?
In the Precordillera, I see in recent work published with Luis Benedetto, we see another genera only present in the endemic of Precordillera. We see Infamatina in lower Ordovician. So
okay.
In that time, we found interchange of genera already with Gondwana. Okay. But we didn't see more genera from Upper Ordovician because I think there is they lost the connection with Laurentian by that time.
Yeah. Okay. Thank you, for answering. Are there other questions for Fernando? If not, I will say thank you for the presentation, and we will move on to the next speaker, which is Olev. But I need to shut this window first, and then I should have it here. So the next speaker will be Olev Vinn, Mark Wilson, Michael Glasson, and Nicolas Sapelski, Goby, and escalation in some symbiosis between large colonial animals and their endobionts. And as always, please keep me posted if there's no sound.
I'm going to talk to you about symbiosis in the Ordovician and the escalation of this process.
I hear sound. Do you guys hear sound? Fantastic. Great.
In the Ordovician, there were many large colonial animals with calcareous skeletons. The major large colonial animals were bryozoans, corals, and stromatoporoids. Large colonial animals with massive skeletons often contained various symbiotic endobionts. Symbiotic endobionts of colonial animals appeared in the Darwinian of Estonia in bryozoans. Bryozoans. All bryozoans are filter feeders that sieve food particles out of the water using retractable lophophore, a crown of tentacles lined with cilia. Ordovician bryozoans lived in various marine environments, often associated with carbonate platforms. Bryozoan colonies vary in shape. Many bryozoans had massive skeletons. Major diversification of group took place in the Darwinian, and first bryozoan endobionts appeared in the Darwinian too. The earliest bryozoan endobionts are known from the Kundan stage of Estonia. Tabulate corals and rugal corals. Tabulates and rugosans were micropredators which presumably fed on zooplankton and killed their food with nematocysts. Ordovician corals lived in various marine environments and were especially common in carbonate platform environments. Corals with massive skeletons are very common in the Ordovician. Major diversification of the group took place in the Cambrian. First symbionts appeared in the Cation. Here on the photo you can see a typical Ordovician tabulate from Laurentian. Stromatoporoids. All stromatoporoids were likely sponges. They all were suspension feeders. Typical Ordovician stromatoporoids had massive skeletons. They lived in various marine environments. Sediments associated with carbonate platforms are especially rich in stromatoporoid fossils. Number of stromatoporoid genera did not change rapidly in the Ordovician. There is not a period of especially high diversification of species in the Ordovician. First symbiotic endobionts appeared in the Cambrian of Laurentian. Symbiotic endobionts in the Ordovician. Skeletal endobionts, which have their own skeleton, are convoluted tube worms with 4 species, conularids with 1 species, gastropods with 4 species, rugose corals with 11 species, and some unknown tuberculous organisms with 1 species. Bioclaustrations are represented by Anoigmaichnus 3 species, Cytosalpinx 1 species, Helicosalpinx 1 species, and large unidentified bioclaustrations, several species, which still are have to be described. Among skeletal endobionts, cornulites are important group. On the upper right corner, you can see photos of cornulites intergrown with the bryozoans in the Ordovician of North America, and cornulite in a tabulate coral from the Cation of Estonia. Cornulites are extinct order of encrusting animals from the Tentaculita class, which were common around the globe in the Ordovician to Devonian oceans and survived until the Carboniferous. In the Ordovician, cornulites and conchicolites were endobiotic symbionts in stromatoboroids, tabulates, and trepostome bryozoans. The earliest symbiotic cornulites appeared in the Sunben of Baltica. Conurarids are also an important group of endobionts. Conurarids are extinct group of fossil cnidarians. Conurarids appear in the fossil records in the latest Vicarian, and they went extinct in the Triassic. Conurarids form symbiotic associations with several trepostome bryozoans in the Ordovician of Baltica. The exact type of symbiosis between trepostomes and conurarids remains unresolved, but most likely the associations were slightly parasitic or commensal. On the left, you can see a figure of stratigraphic distribution of conularid and bryozoan associations in the Ordovician of Baltica. And on the right, you can see conurarids growing inside the trepostome bryozoans. Rugose corals. First endobiotic rugose corals appeared in the Cation of Baltica. Rugose corals form symbiotic associations with trepostomes and cystoporate bryozoans in the Ordovician. It is possible that rugose and bryozoan associations may have been mutualistic. Symbiosis between rugosans and bryozoans was most likely facultative in the Ordovician of Baltica. Now about bioclaustrations. Anoigma ichnus is a bioclaustration in bryozoans. It includes shafts perpendicular to their host growth surface or tilted up to 45 degrees, conical to cylindrical, circular to oval growth sections, lacking separate wall. Their apertures are elevated above their host growth surfaces, forming short chimney-like structures. Anoigma ichnus is the world's earliest known macroscopic endobiotic symbiont that appeared in the Darwinian of Baltica. Anoigma ichnus may have been a parasite. On the photo, you can see a type species of Anoigma ichnus in a trepostome from a Darwinian of Estonia. Cytosalpinx is a bioclaustration, most common in corals, but Ordovician known only from corals. It includes straight to sinuous cavities that are parallel to host axis of growth. The cavity is circular to oval in cross-section, and it lacks wall or lining or floor-like tabula. Cytosalpinx occurs in the tabulates in the Cation to Laurentian, both in Baltica and Laurentia. They may have been parasites. Another bioclaustration known from the Ordovician tabulates is Helicosalpinx. It occurs only in the Ordovician of Laurentia. The trace forms a tight helical to sinus cylinder throughout its length and tend to be sinistrally coiled. On the right on the photo, you can see a typical Helicosalpinx in a tabulate coral from the Cation of Laurentia. Dynamics of symbiotic relationship. Intensity of biological processes can change with time. Intensity of predation, for example, has generally increased over the time. And there have been many speculation whether the symbiosis is a process similar to the predation. And what we found is there was escalation in symbiotic relationship in the Ordovician, so that the large colonial animals in the Cambrian were more symbiotic than in the Darwinian, and the Cambrian ones were more symbiotic than the Cambrian ones. We also discovered a drop in symbiotic relationships in large colonial animals in the Laurentian. In the Rhodanian, symbiotic relationships in large colonial animals recovered to almost Cambrian levels. What we can see on this graphic, there is an increase in symbiosis from the Darwinian to Cambrian and sudden drop in the Laurentian, most likely due to the mass extinction. Explanations for escalation in symbiotic relationships. It may have been evolutionary advantages to have mutualistic relationships. Species with mutualistic relationships may have outcompeted species without mutualistic relationships, and so leading to an increase in mutualistic species. It is also possible that infestation strategies of parasites likely improved with time, and it is possible that at faster pace than anti-parasite strategies of their potential hosts, leading to an increase in parasite-infested species. Invertebrates which sought refuge from predators may have reacted to an increase in predation pressure with a more intense search for a substrate suitable for endobiotic life mode. It is likely that all these three reasons are behind the escalation of symbiotic relationships in the Ordovician. Globe and the evolution of symbiotic relationships. One can speculate that mutual symbiotic relationships may have influenced in diversification of animals by generating new morphologies, physiologies, and behavior for cooperation. Similarly, parasites may have fostered the evolution of anti-parasite morphologies, physiologies, and behavior. However, our analysis did not find any increase in symbiotic relationships before the increase in diversity of host group. In contrast, it seems that the increased diversity of the host group contributed to the evolution of symbiotic relationships, probably due to the creation of new ecological niches. We were not able to control whether the symbionts had a similar pattern, but it is likely that the symbionts also did not show increase in diversity before the increase in symbiotic relationships. Permanent decline in symbiotic relationships. It may have been due to drop in sea level and resultant decrease in host number and diversity of groups that lived in most shallow and therefore most affected environments. It is possible that an environmental stress may have terminated non-obligatory mutualistic relationships. Species with large macroscopic virulent parasites may have been more prone to extinction than the species without such parasites. The end Ordovician climatic change and mass extinction affected symbiotic relationships selectively depending on the taxonomic group of host organisms. The latter discovery is very interesting. Thank you very much.
Thank you, Olev. That was a nice talk. I don't know if there's any questions apart from the one from Stephen Kershaw on the chat. I don't know, Stephen, do you want to ask the question yourself, or should I just ask it? Stephen has a comment, but then he also has a question. Please, can you say what is the evidence that bioclusterations such as, and this funny genus name, were parasitic? Thanks, Steve.
Yes, the reason why we think these bioclusterations are parasitic is because they cause certain damage in the first phase of infestation to the host organism.
Okay, on behalf of Stephen, I say thanks for the answer. Are there other people who have questions for Olev? Yeah, Johan has a question.
Hello, I'm Joan, and I have a question about the symbiotic relationship between stromatoporoid and others. In the case of Estonia, I think it will be same as other paleocontinents. The symbiotic relationship record from, I mean, the symbiotic relationship between stromatoporoid and other organisms or start from the Extinction or more earlier. I just wonder in how it records in Estonia.
In Estonia, it's starting in the Cambrian, but the earliest records are from Laurentian. These are from Cambrian.
Okay, thank you.
Okay, thanks, Johan. Are there other questions? If not, I think we should just thank Olev for all of this session speakers. And then we should go for our coffee break. I will try and create some breakout rooms, as I mentioned earlier, and we will see how it works. And even if it works or it doesn't work, then we will meet again in about half an hour. So that will be 12:30 UTC time. I have no idea what time that will be locally for all of you, but yeah. So I will just go ahead for this.